Why do the vibrations of OH, CO, C double bond O show up strongly in infrared spectra while C to C vibrations do not? And the reason is because the C to C bond is actually non-polar, whereas these ones are polar. There is a dipole across them because oxygen is more electronegative than carbon and oxygen is more electronegative than hydrogen. And so we get strong vibrations from from the bonds that are polar. Figure 7.12 shows the infrared spectra of ethanol, ethanol and ethanoic acid. So let's just draw out the structures of these then. So first of all, we'll start off with ethanol. Eth means there's 2 carbons in the chain, and ethanol means it's an alcohol, so it's got this OH group on there like that. And then we've got ethanal, which is an aldehyde, which means it's got a C double bond O, a carbonyl group on the end of a carbon chain. In this case, it's a 2-carbon chain. And then we've got ethanoic acid, which has got the carbonyl and an OH there like that, next, on the same carbon there on the carbon chain, and like that. So here we have it then. So we've got ethanoic acid, ethanal, and ethanol. Which vibrations give rise to the peaks marked A to G? Now, all these compounds are going to have the C to H bond. And this is one of the things you need to be able to recognise. It says it in the video which one it is. And if you actually had a look at the C to H bonds, and there's loads of them, but they're all, if you have a look around here, we're expecting things around 3,000-ish. We don't have to get bogged down into the details of all this, but if you remember that around 3,000 you've got the C to H bond. So let's have a look at these spectra. Now around 3,000 here, so that's 2,000, that's 4,000, around 3,000-ish there, maybe a bit less there. We've got this series of peaks here. So that would be due to the C to H. Similarly here, in the same position, we've got the C to H. And if we have a look here, so around 3,000-ish, we've got the C to H. Now, but the problem here is that it looks different to these because it's been swamped by this very broad peak here. Now, this is another one you need to be able to recognise. If you've got this really broad, it says in the video, it's like a cucumber. If you've got this like cucumber-shaped peak here, very broad, quite strong, that's the OH that comes from a carboxylic acid. So it's the OH bit from here that we see that's broad. But in being broad like that and strong, it swamps the CH. But the CH is buried there like that. So the next thing we can look at then is let's have a look at the alcoholic OH peak here. Now if we had a look on our table, we would see that the OH for alcohols and phenols is around 3,750 to 3,200. Now it's in a similar kind of region to the carboxylic acids. The only difference is the carboxylic acid one is very much brighter, like we've said. So it's in roughly the same position as the carboxylic acid OH, but it's narrower, and in the video it says like a thumb. So you can imagine this being like a thumb, this being like a cucumber there, like that. So that's the OH there, the OH stretch there. And so it's broad, but not that broad. And it's around this area. You don't really see anything else in this kind of area here other than the OH that you need to worry about. Now, this one has got a peak this small, but it's quite weak. And for an OH, you'd get a strong peak, whether it's a OH from a carboxylic acid or an OH from an alcohol, you get a strong, and this is quite weak there. So we would assign that one to that because it's got the CH and it's got the OH. Next peaks we need to learn. So that A there then is the OH from the alcohol, and that one there, OH. E is the OH from the carboxylic acid. Now the next really key peak, and this is a really important one to be able to recognise, is the carbonyl peak. Now only 2 of these molecules have got the carbonyl, that's the C double bond O. So we'd only expect to see it in 2 of the spectra. And the carbonyl, if we have a look at the table, the carbonyl here comes around 1700. So we're looking for something around 1700. So we are looking for something around here. So this peak here is due to the carbon. So around 1700. It's very strong. It's often the strongest peak there is. And it's around 1750. Now sometimes you see it like that, and sometimes you just see it as a single peak like that. So that's the kind of thing we're looking for. Now if we can see it there, and we can see it here. But we cannot see any such peak here. It would be around 1700, it would be around there, and there's nothing strong there like that. So that confirms really that that's due to the alcohol, because it hasn't got the C double bond O. Now these ones that have got the C double bond O, that one's the carboxylic acid, because it's got this broad OH peak here, which is absent here. And that one there is the aldehyde, like that. Which spectrum belongs to which compound? Well, we've done that. Why do two of the spectra have broad peaks at wave numbers between 3000 and 3500? So we're talking about the OH peak there. And why do they have broad peaks? It's because of the hydrogen bonding. In the alcohol, you get hydrogen bonding, and that leads to this broad peak. Now, you get stronger hydrogen bonding in the carboxylic acid because you've got, as well as the OH group, which can form hydrogen bonds, you've got the C double bond O, which has got a lone pair on the oxygen, which can also form hydrogen bonds with the OH group from another molecule. So there's greater opportunities there for hydrogen bonding in the carboxylic acid, and that leads to a broader peak. The infrared spectrum of a sample of propanal prepared by oxidation of propan-1-ol contained weak absorption at 3437, so in the region where you get the OH peak, suggest two possible reasons for the appearance of this absorption. So why are we getting the OH peak in this sample of this that's been made from that? Well, one of the reasons could be we could have some unreacted OH, propan-1-ol in there, or we could have actually some water, because if you think water as a contaminant, water has got the OH there. So a lot of samples have this OH, but it's because there's a little bit of water there. It's an impurity. Suggest reasons why it is better to use infrared spectroscopy to check the purity of a liquid product from a synthesis than to measure its boiling temperature. Right, well, you can get materials that have got similar boiling temperatures. That's the first thing. So you can't just do a boiling point on something and confirm the identity of it just from the boiling, because there are materials that have got similar boiling points. Also, boiling points do vary according to pressure, atmospheric pressure. And if you're living in somewhere like Boulder, Colorado, which is high altitude, things will boil at a lower temperature than they would be if you were at sea level. So you can get some variation there. And also, when you look at spectroscopy, this region here, which we don't tend to use very much, is known as the fingerprint region. So that is, like it says, it's very identifiable for the compound. So if you've got a standard compound that which you know for sure is the compound you're interested in, and you look at this region here, if you're seeing peaks that aren't in the standard, you can be pretty sure that that's an impurity peak. So this will give you a lot more information about the purity of a sample than just getting a single figure for a boiling point.